Hi everyone, this video is about problems on building. As we know, there are three kinds of building questions: midship compartments, end compartments, intermediate compartments. So this one is on intermediate compartments. So it's a past paper from MMD. So let's see how is this question. Box shaped vessel 160 meter by 18 meter floats in salt water at an even keel draft of 6.4 meters. A forward hold of length 25 meter whose aft bulkhead is 40 meter aft of the forward perpendicular and is built. Permeability of the hold is 80% and kg is 4.7 meter. Determine forward and aft draft in the final condition. So this location of the compartment is forward. Forward means forward of center of flotation. What's the length of the hold? 25 meters. And the aft bulkhead is 40 meters aft of the forward perpendicular. So this is forward perpendicular and this is aft perpendicular. So I have here the diagram. The bottom diagram is the side view and the top is the plan view, top view of the bird's eye view of the water plane area. So here is the forward hold. This is the aft bulkhead. ABSD is aft bulkhead and this is the forward bulkhead. The permeability is 80%. So 80% of the volume of this hold below the water level means up to the draft, up to the original initial draft, that is lost as per the Bilging. So as we know that the ship must continue to displace the weight of water equal to its own weight. Weight has not changed. The ship's weight has not changed. So the ship has to displace the weight of water equal to its own weight. The compartment which is built, so this volume which is 80% of this compartment below water level is not contributing now to the buoyancy of the vessel. So this volume which is lost must be regained by the vessel. So the vessel will sink below the water further. There will be increase in draft and the volume loss will be regained. So the green shaded region between the two water lines, original water line WL and the new water line after building W1L1. So between these two water lines, I have this green shaded area portion, which is a volume regain. So what is how do we find this volume regain? So what we need to multiply the intact water plane area with the sinkage, and that will give the volume regain. But as we are aware that the volume lost must be equal to the volume regained, because the vessel must displace the same uh, amount of water which it was displacing before, equal to its own weight. So there are two things happening here. First of all, to regain the volume lost, the vessel sinks further. S is the sinkage here. This will change the kb. Kb in a box ship vessel is half of the draft. So draft has increased now. So kb will also increase. It will change. Now the hole which is built is forward hole, is forward of center of rotation. So there was certain volume which was earlier providing buoyancy of this hole, but now is lost. It's no more part of the ship. So, since it's no more part of the ship and volume, underwater volume is lost, center of buoyancy, which is the center of gravity of underwater volume, has to change. So where will it shift? Since the volume is lost, it must shift away from the lost volume. So the volume loss is from the forward part, forward of center of rotation. So center of buoyancy will shift off from B to B1, and thereby BB1 creating a trimming lever BB1. So you can see now there is a couple formed. Buoyancy force acting upward from the new center of buoyancy B1. Center of gravity remains where it was before because no change in the weights on board, and the weight is acting downwards. So we have a couple, and it's quite clear that this couple is going to trim the vessel by hand. So forward draft will increase. How do we proceed with the solution? So let's see what was the underwater volume of the ship. It's a box ship vessel, so length into breadth into initial draft, original draft, 160 by 18 into 6.4, 18432 meter cube. And as we said that this is not going to change because after building, the ship will have a sinkage, the draft will increase, and again the underwater volume will be back to 18432 meter cube, what it was before when it was before building. And since underwater volume remains unchanged, of course the displacement W remains unchanged because volume into density of the seawater is displacement, no change, no change. Displacement is not changing, so obviously the kg also no change. But what is changing? Because the water plane area has changed now. We have lost some water plane area after building. So the center of flotation will also now shift in the same manner as center of buoyancy has shifted aft away from the lost volume. The center of flotation will also shift aft away from the centroid of the lost water plane area, which is in the forward part. So we have to now find the new BML because center of flotation is changed because BML is moment of inertia upon underwater volume. So let's proceed. Sinkage, as you know, is volume of lost buoyancy upon intact water plane area. So that is 0.80% of the volume of this hole, which was below the water level. So length of the hole 25, breadth of the hole 18, and initial draft 6.4 meter. This is the volume of the hole below the water level, initial water draft. 80% of it, so 0.8 multiplied is lost. This is the volume of lost buoyancy. What is the intact water plane area now? Total area, length into breadth of the hole of the ship, 160 by 18, minus lost water plane area. So what is the water plane area? It is the length of the hole multiplied by the breadth of the hole, 25 into 18, and 80% of it because there is permeability of 80%. So 0.8, the length of the hole and into breadth of the hole. This is lost. So if I subtract from total area the lost area, I get the remaining intact area. So 2304 is the volume of lost buoyancy, and 2520 is intact water plane area. I get sinkage 0.914. Okay, now to find the new center of rotation, F1. The original center of rotation is F, and which has shifted now aft from F to F1. It is on the calculation, there is a formula for GG1 when we discharge some weight from the ship's center of gravity G shifts to G1. What is the formula for that? It's a simplified formula from the moments, and it is a W, small w, which is weight discharge, into D, with distance between the center of gravity of the hole and the center of gravity of the ship. That is D divided by the final displacement. The same formula here. Here we have, instead of the weight, we have area. So area lost, which is permeability into length of the hole into breadth of the hole. That is the water plane area lost, multiplied by the distance between the centroid of the area lost and the center of flotation of the original water plane area. X here, marked here as X. This is the distance between the center of flotation and the centroid of the water plane area, which is lost, divided by intact water plane area. You can do it many ways. You can take moments from the aft perpendicular and you will get the new center of flotation from aft perpendicular, LCF1, or you can do like this, the way I have done. It will give the how much the center of flotation has shifted towards aft from F to F1. So 0.8 is the permeability, 80%. Length of the hole is 25 meter. Depth of the hole is 18 meter. This is the area lost. And 52.5 meter is the distance between the, like you can say, the center of gravity of that hole and center of flotation, or the centroid of the water plane area lost and center of flotation. Is you can study this diagram here. So this is the aft bulkhead. It is 40 meters aft of the forward perpendicular, and this is midship, where the original center of flotation is at midship. So from center of flotation to forward perpendicular is half of the ship's length, which is 80 meters. So of course, then if the aft bulkhead is 40 meters aft of forward perpendicular, then remaining is another 40 meters to the center of flotation, F. And the centroid of this water plane area, which is lost, will be halfway, half of its length, half of the length of the hole, because it's a rectangle. So half of the length of the hole will be 25 by 2, which is 12.5 L by 2, and plus 40. So from center of flotation to the centroid of this lost water plane area is 40 plus 12.5 is 52.5. Okay. So that is used here. Water plane area lost into distance of its center of gravity from center of flotation. Original center of flotation is 52.5 upon intact water plane area, which is found here 2520. So I get 7.5 meters. 7.5 meter is the shift in the center of flotation towards aft. So what is LCF1? Originally center of flotation was 80 meters from aft perpendicular, because length is 160 meter. Now it has shifted 7.5 meter towards aft. So LCF1 will be 80 minus 7.5 is 72.5 meter. That is the distance of the new center of flotation F1 from aft perpendicular. And new draft is original draft 6.4 plus sinkage 0.914, 7.314. Now, as we have discussed that there will be a change of trim. For change of trim, I need MCTC. It's not given in the question, so the formula is W into GML upon 100 into L. So W is the displacement, which is not changed. I have it. GML has changed. I don't have it. So GML is the longitudinal metacentric height upon 100 into ship's length. So how do you find GML? GML is KML minus kg. Kg has not changed. KML is KB plus BML. So this is important here. KB plus BML. It's a box ship vessel, so KB will be half of the new draft. That's okay. But for the I need BML of the intact water plane area. So BML of the intact water plane area will be IL, which is moment of inertia of the water plane area, longitudinal moment of inertia of the water plane area about the axis passing through the new center of rotation, which is F1, because F1 is the center of rotation of the intact water plane area, divided by the underwater volume, which is still the same. So moment of inertia of the intact water plane area will have to be found by adding to by subtracting the total water plane area minus the lost water plane area. So moment of inertia of the initial water plane area means total water plane area, but about F1, because when we need moment of inertia about new center of rotation, which is F1. So all moment of inertia I have to recalculate about F1 and then minus the moment of inertia of the lost water plane area. That will give me IL of the intact water plane area. Was the water plane IL of the initial water plane area means the total water plane area about F1. See, BL cube upon 12, that initial breadth and length of the water plane area total. BL cube upon 12 will give me the moment of inertia passing about the axis passing through the center of rotation, the original center of rotation. But I need about F1. So I have to use parallel axis theorem plus AD square. A is the area of the water plane, 18 into 160. And D is the distance between the two axes, means the distance between the original center of rotation and the new center of rotation, F and F1, which we have found 7.5 meters. So D square, 7.5 square. Okay, it is like BL upon 12 plus AX square. X is the distance between the new and the old center of rotation. So this gives me the moment of inertia of the total water plane area about the axis passing through F1, this formula. Then I find the moment of inertia of the lost water plane area again about axis passing through F1. So if I do the BL cube upon 12 means breadth of the hole into length of the hole, cube of the length of the hole, this is 18 into 25 upon 12. This will give me moment of inertia about the axis passing to the centroid of the hole. But I need the moment of inertia about the axis which is passing through F1. So I need the distance between the centroid of the hole and F1, which we have found that is 60 meters. So you can see here. So from F1 to the centroid of the hole, center of gravity of the hole, we are talking about now. Between F and F1 is 7.5 meter. So from center of rotation to the aft bulkhead of the hole is 40 meter. Then the centroid of the hole will be half of its length because it's a rectangle. Length is 25, so half will be 12.5. So we have 7.5 plus 40 plus 12.5. This total, if you take from F1 to the centroid of this hole, center of gravity of this hole, it will be 60 meters. It's just a simple arithmetic which you can find. So we were at moment of inertia IL of the lost water plane area about F1. So that will be the moment of inertia will also be have to multiply by 80% because it's 80% only we have lost. So 0.8 is the permeability I keep outside, and in the bracket I have BL cube upon 12 plus again AD square. And here BL cube upon 12 is breadth of the hole 18, length of the hole 25, area 18 into 25, and D square, as we saw, D is the distance between the centroid of the water plane area lost and the new center of rotation, F1. Parallel axis theorem, D square is the distance between the two axes. One axis is passing through the centroid of the hole, and the second axis is passing through the F1, the new center of rotation. That distance is 60, so it becomes 60 square, and we get this value 1314,750. So subtract to get the intact IL of the intact water plane area about F1. So total moment of inertia which we found here minus the moment of inertia of the lost water plane area gives me this value 4991250. I got the moment of inertia now. I can find the BML of the intact water plane area. That's moment of inertia of the intact water plane area 4991250 upon underwater volume, which is same as before 18432, and I get 270.793 meters. That is the BML of the intact water plane area. KML is KB1 plus BML. The new draft is 7.314 by 2 D by 2, that is new KB1, and new BML is found 270.793. KML is 274.45. GML is KML minus KG, so 274.45 minus 4.7, we get 269.75. This is the GML I insert here in the formula for MCTC. So displacement W, which is unchanged, 18892.8, GML 269.75 upon 100 into LBP, which is 160 meter length of the vessel. So get MCTC 318.521 ton meter. Change of trim is trimming moment upon MCTC. What is trimming moment? So here the trimming moment is caused due to the lost volume of the buoyancy, which has caused the center of buoyancy to shift aft. So the volume of the lost buoyancy, we can convert it into weight of the water which has entered the hold. So volume of lost buoyancy into density of salt water 1.025. This is in terms of weight of the water which has entered the hold. And tipping moment is always you have to multiply by distance from center of rotation. So distance from F1 upon MCTC. So volume of lost buoyancy is 2304 meter cube multiplied by the saltwater density 1.025 multiplied by the distance of the center of gravity of the bilged hole and the new center of rotation F1. The distance from the new center of rotation to the center of gravity of the cargo hold, which is built at 60 meters. So this is the trimming moment divided by MCTC 318.521. This gives me change of trim 4.448 meters. Then from this formula, you will get it in centimeters, but you can divide by 100 and you can get it in meters, 4.448. And the standard formula to find the change in draft aft, trim aft will be change of trim into LCF1. So new longitudinal center of rotation, which is F1, into change of trim upon LBP. Change of trim is 4.448. LCF1 is found as 72.5 meters. Now divide by 160, 2.015. And trim forward will be total change of trim minus trim aft. So 4.448 minus 2.015 gives 2.432. This is trim forward. So the original drafts were 6.4 meters forward and aft, even keel. Mean sinkage due to bilging was 0.914 plus 0.94 plus 0.914. Now TA and TF, as you know, the ship has trimmed by the head, so forward draft will increase, so plus 2.432 TF, and aft will decrease due to change in the trim, minus 2.015 TA, and this gives final draft forward 9.746, aft 5.29. This is the working. So I hope you find it useful and I'm able to explain. If there is any question, you can always put it in the comments and I will answer. Right? Thank you very much.